the extent to which, right, you start with a relatively large size and you're decreasing in size as you go across the periodic table. And then, right, as you go up in your periodic table, so as I go from period 3 to period 2, right? What's the difference in size? Am I getting smaller or larger? So this is period 2. This is period 3. What's happening? What do you notice? So if we're thinking about that from just a general standpoint, right, we want to make sure that as we start to think about trends in our periodic table, that we can identify how they change as we move across a period, and then as we move down a group or up a group. So for example, if I'm comparing, let's say I'm comparing lithium and sodium. So lithium, right, is what I see in purple, that's right here. Sodium is what I see in green, that's right here. So as I'm moving up a group, my atomic radii decrease. Right? So notice here in period 6, 235, that's my largest atomic radii. As I move up to hydrogen, that's going to be my smallest atomic radii. As I move across, right, what's my trend? So take a moment and think about moving from left to right and whether that's increasing or decreasing. And then think about moving either from top to bottom or from bottom to top. My recommendation is that you pick 2 directions, so either left to right and top to bottom, or right, another combination, and start to think about what the trend is for atomic radii as you move across. So if you think about it, Heba asked a really great question. She said, so atomic size always decreases as we move left. And that's correct, right? So if you're thinking about this pattern, lithium, the farthest left is 123. If I move across to my fluorine, that's 64. That's my smallest. Right? And then in this case, I'm increasing in size as I go from the top of the periodic table to the bottom of the periodic table. So part of the reason why we graph these numbers and we start to visualize our periodic trends is because there's a lot actually of ways that we can think about periodicity. And really this idea of periodicity is just, hey, how do I make sense of the grouping or the patterns that I see in the periodic table? So let's take another look. Sometimes we can visualize one way, and if we visualize a different way, it helps us see things a little bit differently. So we're going to do the same thing, but now we're going to think about our periodic table with respect to our cations and anions. So if you're looking at your periodic table, here's what I want you to think about. Lithium, when it gives up an electron, do you think that's going to be larger or smaller? Right? And because it's giving up that electron, it makes sense that it becomes smaller. You're taking something away from lithium in order to form the lithium cation. Likewise, if you're thinking about this, say for example, for the anions, right? Anions start small, but then get bigger because they're gaining an electron. So we have to think about the reason for this. So if we have the number specified, right? Why is it? Well, for cations, it's because we're taking an electron away. And then if we're thinking about it in terms of anions as to why they're bigger, that's because there's electron-electron repulsion that actually causes those electrons to spread out in space. And so they're actually going to get bigger as we add electrons, and they're going to push each other further away. So as just a quick knowledge check, here's what I'd like for you to do. On your whiteboard or in your notes, go ahead and draw out the electron configuration for fluorine. So in your notes, go ahead and draw out the electron configuration for fluorine. You can also do it on a whiteboard. And while you're at it, go ahead and provide the orbital diagram as well. So find where fluorine is. Fluorine's atomic number is 9. So if I take a look at fluorine, one of the things I want you to notice is that when I form my fluoride anion, all I'm doing is adding one more electron. So if I think about my orbital diagram that I filled, remember I'm using the Aufbau principle to fill from the bottom up. So I'm going to fill my 1s first, and then my 2s, and then my 2p. The other piece here that's really important is that because of Hund's rule, my fluorine, right, my atom that I would find as the neutral element in my periodic table, that's going to have 5 electrons in the 2p orbitals. But if I'm forming fluoride, I'm going to add one more. Right? And so now my fluoride, or my F minus, becomes like my noble gas. So if I'm thinking about it, my fluoride ion, or my F minus, becomes like neon, which is the reason why we form cations and anions really in the first place, is that by forming those ions, I'm creating a more stable atom. Okay, I'm gonna go back to sharing my screen. Here's what I want you to think about. So if we're thinking about then the size of our ions, I want you to think about if we're starting out and it's something that's already pretty big, right? I want you to think about what happens then if it forms an ion, right? And for that reason, right, as you start to think about size, that might change the way that it behaves. So if you think about, for example, lithium starting out, right, as pretty sizable, once it becomes a cation, right, and it has that positive charge and it gets smaller, maybe lithium as an ion can fit into places. Say, for example, it can fit into receptors on proteins that it otherwise would not be able to fit into when it's lithium, the neutral atom. So that's the reason why we're starting to think about electron configurations, and specifically the periodic trends, is because the structure of our atoms are going to change the way they behave or to change their function. And so when we think about structure, we know that there's a very close relationship to function. Okay, here's another really cool representation of that. So I want you to take a look at this diagram. On the right-hand side, this is the size of a 1s. This is the size of a 2s. And this is the size of a 3s orbital. When you think about that size, I want you to think about the fact that that's really the representation of where you're most likely to find electrons. So if you were going on an electron hunt, it would be pretty easy to find an electron in your 1s orbital. But if you were going on an electron hunt, say for example, in your 2s or in your 3s, right, it might take a little bit more time for you to be able to find that electron because it could be anywhere, right, in this space. And so when we're representing our orbitals, right, whether they're circles on our orbital diagram or squares, really what they're representing is population density. So where am I most likely to find my electrons? So here, right, if we're thinking about atomic radius, why are lithium, sodium, potassium, rubidium, cesium, why do you think of those, right, having the largest atomic radius? And then why would helium, neon, argon, krypton, xenon, right, our noble gases, be quote unquote so small? So I want you to think about that. We're going to come back to that actually when we come back from spring break. We'll have a really cool activity that helps us think about, as we go from left to right across the periodic table, how behavior changes. But for now, I want you to start to think about how that might change. I also want you to notice here we have our period 4 and period 5 transition elements. So if you're looking at your periodic table, one of the things that's really important for us to notice is that if you're looking, say, for example, at row 4 or period 4 in the periodic table, if you go across and you get to the D elements, that's actually our 3D orbitals. So I think Nikayla, or maybe it was Skylar this morning, had a really great observation. They're like, wait a minute, the numbering changes. And that's because we squash our periodic table together so that it fits on a page. But if you were to actually draw it out, it would be really wide in order to fit our D and our F orbitals. So we squash it together for the sake of convenience, but you can actually see here, right, our period 4 transition elements and period 5 transition elements actually take up that space. So it gets, right, longer as we take a look. Okay, got one more activity that I'd love for you to take a look at. So we're going to do the same thing. This is atomic radius. And again, we use diagrams in order for us to be able to make sense of numbers. Right? We use a representation visually to help us make sense of information that sometimes our brains can translate in terms of numbers, but sometimes our eyes might see differently. So on your left, right, is the relative size of the atomic radius. And here, I want you to think about if you had to scale that. So for example, right, if you were to draw that, and this is, right, 1 would be 1 centimeter, right? So this would be 1.5 centimeters. What would that actually look like here? So if you had to visually draw that, right, and you were to draw it as a sphere, what would it look like? So I think that it's one of those things where it really is helpful to be able to think about how to visualize the numbers that we see here. And so I want you to take a minute and try doing that. So take a minute and go ahead and draw out what you see. So Raquel asked a really great question about atomic size. So atomic radius, if you think about it, right, the radius of a circle, right, is the distance from the center to an edge. And so if we're thinking about atomic radius, that tells us something about how big our sphere is of our atom. And so if we think about atomic size, then yes, they're going to be very closely related. So the size, right? We could measure size as the diameter, say, for example, of an atom, or the radius. But atomic size tells us something about how big it is. And more often than not, that's represented as the radius. Okay, so let's take a look. Okay, let me go here. Maybe I can show it that way. All right, so you should have something that starts to look like this. And so maybe this is a better way for us to be able to visualize relative size. So if we're thinking about relative size, this is a great example. You can actually see, oh, look, right? My hydrogen, that's pretty small compared to, right, my calcium. So this isn't a complete periodic table, but it's enough for you to start to see that, right, as you go down, you see pretty significant changes. As you go from left to right, right, your, say, for example, 3, 4, and 5, those are some small differences. They're starting to decrease in size, right? And then if you think about, say, for example, column 7, right, I definitely see an increase in size as I go down. So in your notes that I shared for today, and in the PDFs that came in the email, you can actually do this for any one of the trends. And so one of the questions that I'll ask on your exam 2 will be for you to visualize the periodic trends. And so this is a great way to practice doing that. You'll have lots of choices in terms of how you visualize those trends. But this is one of the approaches that you can use. And I think it's helpful because sometimes when we talk about size, we need a reference point in terms of numbers, or visually it can be really helpful to be able to try and think about how to represent that. So for the moment, I'd love for you to take a different example. So in the PDF, you actually have several to choose from. So we did atomic radius, but you can choose something else. So ionic radius or ionization energy. And what you're going to need then is the data. So if you're taking a look, let me scroll up so you can see. So you can use this as representative symbols. So you have a choice: atomic radius, ionization energy, ionic radius, or electronegativity. You don't have to use these symbols, you can choose something else. But it gives you a reference point. So for example, if we think about our scale and the way we're representing information, our 1 centimeter is equivalent to roughly half an angstrom. So what we're doing here is modeling what we see that we can't actually see in person, right, with the naked eye. So that's going to be something that's super helpful, I think, for you as you're starting to think about your periodic trends. So go ahead and take a moment, and in your notes or on your whiteboard, go ahead and sketch out the relative sizes. And if you're like, oh, I'm not sure how to do that as an estimation, for me, when I measure a centimeter, it's about the same length as my smallest fingernail on my pinky. And so that's the reference that I use when I'm drawing. And you'll notice that I don't draw perfect circles. That's okay. Nobody needs to draw perfect circles. This is an approximation. We know that our models have benefits and limitations. One limitation of my model is that my circles are not perfect spheres. And so that's okay. Okay, so I want to make sure that we have time for the next activity. So I'm going to scroll down and show you the next screen. So if you are following along, you're going to want to click on the periodic table of elements because you can actually do this simulation on your computer. So I want you to take a moment and go there. So this is what it should look like. So I'll give everybody a minute to get there. Okay, so if you're scrolling down, here's what I want you to see. You can choose an element. So I chose 2 to compare. I chose sodium and I chose fluoride. And you'll notice that one of the things that I did was I made sodium +1. Right? If I wanted to take that electron away, I literally would click on it and remove it. Right? So this is a good example of the way I would form an ion. And you can actually see then that decrease in size. And then part of what we're going to start to think about is the way in which we can use these to represent, say, for example, our ionic radius. So we'll choose that as the example that we're looking at. And there are a bunch of activities that you can do associated with that. So this is a great simulation to kind of practice and make sense of, right? So for example, let's say I chose potassium and I chose calcium, and I wanted to be able to compare those two. So notice potassium has a slightly larger atomic radius than calcium does. Both of these, if I remove an electron, right, now, right, what does this look like? What does it most closely resemble? And if I look at my periodic table and I think about what I just formed, if I take an electron away from potassium, right, it's going to become argon. Right? Its electron configuration is closest to argon. If I take an electron away from calcium, that's calcium +1, but I actually need to remove a second electron because calcium, right, forms a +2. So in order for calcium to become like argon in terms of its electron configuration, I have to remove 2 electrons to be able to see that. So I want you to take about 5 minutes and explore this simulation. And while you're doing that, I'm going to get my power cord so that we don't lose power. And if you're like, ooh, where do I find the link? I will post it in the chat, and then you can just click on that. So if you're looking for the link for the simulation, you can just click on it in chat. That'll be easier probably than going to hunt and find the slides. Ooh, Zoe asked a great question. She was like, what does it mean that an atom is unstable? So stability, I think, is a great relative term. So there is unstable in the sense that an atom could break apart into its components. So for example, When we think about stability, sometimes we think about the decay of an atom and the way that it releases nuclear particles. But stability can also refer to the atomic orbitals in the sense that something that is a noble gas configuration is stable because it typically has a complete octet. So for example, if I'm comparing neon and argon, um, you'll notice that, right, these atoms are stable because they have a complete octet. And so if I compare argon, say for example, to potassium, right, by taking one electron away, right, I have a much more stable compound because it has a complete octet. Whereas if I, right, put that electron back, you're going to notice that, right, now potassium, it's a lot easier to lose one electron than it is to gain 7. Okay. All right. So while you're working on that, I'm going to see if there are any questions that I missed in the chat. So the question from Heba is, why is the atomic radius for helium smaller than for hydrogen when helium has more electrons than hydrogen? So I want you to think about that for a moment. What might be a reason why, right, hydrogen is larger than helium? The atoms themselves are smaller than the helium atoms, but a molecule of hydrogen is actually made up of 2 atoms that are connected by a bond. And so a hydrogen molecule is going to be much larger than a helium molecule. And so if we're thinking about that, then that's part of the reason why we observe that. And then if we're thinking about helium as an atom, right, compared to hydrogen, that's a different question, right? So if we're thinking about the periodic trends, right, as you go from left to right, the atomic number is going to increase while the valence electrons stay the same. So the answer for that is that there's increasing nuclear charge. So helium has 2 protons, whereas hydrogen only has 1. And so helium pulls on those electrons and draws them closer to the nucleus because there's a greater nuclear charge. So the reason why helium is smaller than hydrogen has to do with the protons, or its atomic number, the number of protons in the nucleus. Okay, so there are some other data visualizations that we're going to take advantage of. And I think I want to share these mostly because there are several ways to think about the periodic trends, and it might be useful for you to explore each of them and to think about which ones help you make sense of these trends. And so we're going to have some additional opportunities to practice when we come back from spring break and we're reviewing for exam 2. But I really want to make sure that you're super comfortable with your periodic trends so you have the chance to explore them over spring break. So here's another representation of the periodic trends. And so I've had students ask, they're like, so what kind of a question are you going to ask me about the periodic trends? And I think the most important part is you could certainly memorize these trends. And I'll be honest with you, at some point in time in my life, I memorized them, and that was how I answered questions about them. But I really think you're better served if you can explain why that trend exists and what the reason is for the trend. So for example, right, we've talked about ionization energy. And so if you recall back to Monday's session, what is ionization energy? Ionization energy is the energy that it takes to be able to remove an electron. So it's probably going to be really easy to remove an electron from this first group. Why? If I remove that electron, what does this atom become? It becomes the really stable noble gases. So my ionization energy here, do you think that's going to be high or low? Right? My ionization energy, what it takes to remove that electron, is probably going to be lower. Right? If I compare that to my ionization energy for something that's completely satisfied and content, right, then my ionization energy here is probably going to be a lot higher. And so it's important that you can give the reasoning or the rationalization for why. Okay, here's another representation of periodic trends in the periodic table. This is done by color. I'll say, I think for myself, I actually have a harder time reading the smaller gradations because my eyes don't do such a great job in terms of differentiating the color changes that are here. But it is really helpful because you can see that not all trends are the same. So for example, right, our atomic radius we know increases as we go down a group, right? And it increases from right to left across a periodic table. What's the trend for electronegativity? Right? If we're thinking about the Pauling scale, and this is a relative measure of, right, how many electrons something has. For electronegativity, what do you think is the trend? Go ahead and take a moment and write out in your notes what you think the trend is for electronegativity. Yeah, thank you, Abigail. Thank you, Dean. It increases going to the right, and it increases going up the periodic table. So do you remember, this was a long time ago, but for the week that we had Valentine's Day, the Bio 310 folks came in and they presented to the class and they gave the Orange Crush soda cans. And when they were presenting in the front of the room, do you remember what one of them said? They're like, fluorine is the most electronegative element. So here's how you know that. This is the reason why fluorine is the most electronegative element, is because it is the farthest to the right and the topmost of the elements. So here's a great example, though, of the ways in which there's still frontiers in science and things that we don't know about. Do you see these circles? Right? Right now, it's impossible for us to measure the electronegativity of these noble gases. So if you wanted to be able to discover something, say, for example, you wanted to do some graduate research, you could actually look at discovering the electronegativities of, say, for example, transition metals or noble gases. Interesting point that I hadn't discovered until I started looking at these resources. If you're British, you spell ionization with an S, whereas if you're American, you spell it with a Z. I hadn't anticipated that. But this is a great example too of, if we're thinking about ionization energy, there are some spaces that are truly unknown and that we haven't been able to study these atoms because they're so unstable. So they're so reactive that they have a tendency to be difficult for scientists to be able to isolate and study because they're not particularly stable. So that's a great example of another representation of the periodic trends. And then I've got a couple more that I want to share with you. This one I think is so cool. So this is a three-dimensional representation, and so it shows you the atomic radius, right? And you can actually see that it slides down and it gets smaller, right? And so if you're thinking about the trend, we increase from right to left and increase from top to bottom for atomic radius. And then isn't it interesting, right? Your ionization energies and the way these are depicted, you can actually see how the ionization energies are very low for the alkali metals, but very high for the noble gases. And you can see the extent to which they really don't change that much if you're looking at our D elements or F block elements. And then I had someone ask in the chat box, what's electron affinity again? And remember, right, electron affinity is the extent to which something wants an electron. So how much does an atom want an electron? That's a good way to think about electron affinity, right? And then electronegativity is how many electrons does it have? So if we're thinking about electronegativity, that's a good way to think about it. So the difference, right? What's the difference between electron affinity and electronegativity? Take a minute and think about that. So electronegativity is the ability of an atom to attract electrons from outside itself to itself, whereas electron affinity is the amount of energy that's released whenever we're gaining an electron. So it's really easy for folks to mix up or confuse those terms. So let's take a minute and make sure that we have a clear working definition for those in our notes. So if we're thinking about it, the difference between electronegativity and electron affinity. So electronegativity is the ability of an atom to attract electrons to itself. And then electron affinity is the amount of energy that's released when a neutral atom or a molecule gains an electron from the outside. So there's always an energy associated with that change. So electronegativity is what we often think of as a qualitative property. It's something that we use to describe, whereas electron affinity is something we can actually measure. So we can measure it in terms of kilojoules per mole, and that can be true for either an atom or a molecule. Okay. Ooh, yes, I can write it in the chat for sure. All right, so super useful for you as well. I want to be able to show you. So if you haven't checked it out yet, it's totally worth checking out chapter 6.5. Yes. So if you check here, there's some really great visualizations for 6.5 in terms of the periodic variations. And so you can do that on your phone or you can do that on a computer. All right, last one. So you can also, right, explore trends to be able to display. So If, say, for example, you wanted to look at a specific type of trend, there's a variety of tools that allow you to see this. So for example, this shows you the density, right, of the atoms. Or if you wanted to look, say, for example, at melting point, you could select that. Okay, so I want to make sure that we have enough time to do two things today. So before we transition, I think I have one more. Okay, no, we're good. Hooray. So there are a variety of ways that you can visualize or represent the periodic trends. Here's the goal. Today, we're just introducing them. Between now and when you're done with Alex, hopefully you'll have the opportunity to practice using them. And then we'll have when we come back from spring break, we'll be able to do a review to make sense of how we apply those periodic trends to certain types of problems. So you'll have the opportunity to be able to review them. I've shared several different tools with you. My recommendation is find one that you think is most useful for you in order to make sense of the trends. And so on an exam, I'm not going to ask you to state the trends because you can look that up. But I'm really hoping that you'll be able to explain the trends. So for example, if I give you this image, I'm going to ask you to explain why the atomic radius increases as we go from right to left. What is it about atomic radii, and why is it that they get larger as we move across the table from right to left? And if you're like, ooh, is she going to ask a claim evidence reasoning statement? The answer is yes, right? You're guaranteed to see that as one of your exam questions. So it's a great opportunity to practice making sense of why, right? Or what's your evidence and your justification for the following trend. Okay, I want to, if I switch here. All right. So I want to make sure that we have enough time to be able to show you the following. So we've got an exam coming up, and I want to make sure that you have a chance to see what that exam looks like. So I'm going to close these guys because we don't need them anymore. And I'm going to pull up our practice exam. So here we go. All right, you have this in the email from me already, but I wanted to talk through a couple of pieces. So hopefully you have a periodic table with you. And I've had several folks who were like, hey, wait a minute, Sloan, how are we going to do an exam when, right, we can't sit down in person and use paper? And so the answer to that is I really want to make sure that you can check and make sure that I'm sharing screen. Yes. Okay. All right. So I want to make sure that you're comfortable with a couple of pieces. So one, the exam 2 is going to be open notes, open resources. So you can use your electronic devices, you can use the internet or interwebs, you can use your notes, you can use the book. There's no resource that's off the table for you. But this exam is time bound. So the way it will work is I will email you the exam, and then what you're going to do is you're going to do your work, and then you'll take screenshots and you'll send me screenshots of your work by the 2-hour mark. So essentially you'll have 2 hours to work on that exam, the same length of time that you normally would, right? So we usually finish an exam in about an hour and 20 minutes or so. So that still leaves you some buffer time if you're still working on problems and need a little bit of space. And then you're going to take screenshots of your work and you're going to send those to me by email. If you're like, wait, take screenshots how? So you're going to use your phone and you're going to take pictures of essentially your work and send that to me. If that's not going to work for you, just send me an email and we'll figure out an alternate. But the other piece is that I thought would be really helpful to talk through is a couple of the components of the types of questions. So yeah, you can absolutely, Arlene asked a really great question about using each other. You can absolutely work together. My intention for exam 2 is that you are as collaborative as possible in terms of this exam. We're really thinking of this as a review opportunity for you to check your knowledge and then refine your understanding. And so the only limitation, again, is you're going to have to make some choices about how you interact with other students. So for example, you're still responsible for answering all of the questions, which means you really have to think about your own personal knowledge. And then, right, collaborate if there are 1 or 2 points that you might need clarification on. So this is different, say, for example, than a take-home exam, and that you don't have a 24-hour window of time. You only have that 2-hour block where you're working on this. So the difference is you really do need to know your material going into the exam, but if there's something that you can't remember, you can always look it up to help make sense of your understanding. Okay, so couple of pieces that I think are really useful to look at here. So you're going to notice that there are a couple of types of questions that we're going to commonly see on this type of an exam. So the first thing that we're going to see is you're going to see gas law questions. So that's chapter 9 if you're thinking about that. Remember, right, standard temperature and pressure, we have a specific definition for that. You can look back in your notes to find that. These questions are always the short answer claim evidence reasoning. I had a really great question from a student, and they were like, hey, do I have to use a specific format? And the answer is no. You could bullet point your claim evidence reasoning statement. You could write it as 3 short sentences. The goal is not for it to be long. The goal is for you to be able to explain your reasoning or explain your thinking as to how you got to an answer. So your claim is however you would answer this question. Your evidence would be whatever work, say for example, the equation that you used or the algebra that you used to rearrange or substituting and solving. Those would be examples of evidence. And then your reasoning are the relationships between those variables. So for example, right, is there a proportional relationship between pressure and temperature, or is it inversely proportional? That's the type of reasoning that you would use. Okay, other examples. So we've done some heat calculations, and remember you have access to an equation sheet that I gave you in class. If for some reason you don't have that, just send me an email. I can always send it out again, and I'll post it on iLearn as well. In addition, right, we're thinking about the relationships between specific variables, say for example in our gas laws. And you're going to be able to work on your long and short condensed electron configurations. And that's actually going to be our quiz today, which we'll talk about shortly. Samantha asked a great question. So yes, my plan is to post the key for the practice exam this weekend. So I should probably be able to get that up by Friday. I'm working on the materials for your discussion tomorrow, but I will definitely be able to post a key for this by Friday. And kudos to you, there will be 3 common mistakes in the practice exam. If you find one of those common mistakes and send me an email, I'll correct it and repost it and give additional points to you. So please make sure that you're scanning and looking at the answers closely to see if you can find those 3 most common mistakes. Okay, so those are the claim evidence reasoning type questions. You'll notice that you're going to have 4 of those, right? So 4 claim evidence reasoning questions. And then here, right, are our longer questions. These don't require a claim evidence reasoning response. All you need to do is show your full calculations. You want to make sure that you box your final answer and that you use the correct significant figures. So this is similar to the structure of what you saw in exam 1. And again, you're going to show your work. And then the last one is you'll have the choice of a choose your own adventure. So you'll be able to choose one of the 3 following to be able to answer. And then I'll also have the extra credit as we had before. So are there any questions about the structure of the exam before we move on? So exam 2, this is a really good question. Thanks, Julian, for asking. So if I pull up, this is a super useful resource as well. If I pull up my iLearn, make it smaller. So if you go to iLearn, one of the things that is useful for you to see is that we made an adjusted syllabus specifically because of the suspension of classes last week. And so because of that, one of the things that I think is really important is that you see the adjusted schedule. So let me pull that up. I thought I had pulled it up. There we go. All right. So make it a little bit larger so everybody can see. Okay. So if we scroll all the way down, the changes to our course are highlighted in yellow. But if we scroll all the way down to our schedule, one of the things you'll notice about schedule is the extent to which we've adjusted the exam. So normally you would be taking your exam right now for exam 2, but because of the changes that we made, so your exam is on the 8th of April. So that's when we come back from spring break. And if you're like, ooh, how am I going to do that when I'm online or at home? And the answer is you're going to show me your work just like you normally would. And then once you show me your work, then I will be able to provide feedback to you just like I normally would. So one of the things that I think is really helpful is for you to be able to get feedback on the work that you're doing. And so our exam structure is so that you get feedback to make sense of your understanding. And so for that purpose today, we'll make sure that for exam 2, you have access to resources. And then our goal here is to get you as much feedback as possible so you have a sense of your cumulative understanding thus far in the course. Okay, so thank you, Julian, for asking that question. Really appreciate it. All right, next thing we're going to do. So if you go to your virtual learning plan, and if you're like, ooh, where do I find that? It's at the top of the page on iLearn. We're going to transition, and I'm going to have you take your week 10 quiz. So the really cool part about this is that it's a new technology. So you're just going to take this link, and I'll put it in the chat box. And you'll click on this link. Maybe if I can move it out. Oh, there we go. You can absolutely print it out in terms of the exam if you want to, or you can also just write it in your notes on line paper. You can print out the exam and work on it in your own hand, and then just take screenshots of it. Okay, so for the quiz, go ahead and click on this link, and it should open up a separate window, and I'll walk you through what it is you're going to do for your exam. Or sorry, not your exam, your quiz. Brain tired today. Okay, so you should, when you click on that link, get a window that looks like this. And your quiz today, you're going to choose an element with an atomic number between 13 and 18. And on your whiteboard or in your notes, something that you can hold up to a screen, you're going to write the condensed electron configuration and you're going to draw the orbital diagram. And so then you're going to record a 90-second video explaining the electron configuration for your element. So that's our quiz for this week. I'm going to hang out here on Zoom while you guys take your quiz. If you have any questions, I'll happily answer them. But this is your time to take your quiz. Hopefully everyone should be able to finish it. It's a 90-second video. I think it should take you somewhere between 1 and 2 minutes to draw your electron configurations, but you have up to about 10. And so that's your quiz for today. And while you're doing your quiz, I'll make sure that I'm answering the questions in the chat. So if you're working on your quiz, go ahead and upload that through Flipgrid. So you'll create your condensed electron configuration. That's the same thing as the short electron configuration. So that's where you're using the noble gas in brackets. And then all right. And then once you're done with the quiz, you can stay and I will happily support for your office hours, or you are welcome to email me, or you can chat me, or we can have an extended conversation during office hours later on this week if that's better for you too. Okay. If you're like, ooh, I'm having technological difficulties, don't worry. You can also just write your electron configuration and your orbital diagram, and you can send that to me by email. That's totally fine as well.
Just a reminder, everyone, S-Cube does have the session today from 12:30 to 1:30. The link is on iLearn underneath the class lecture Zoom. So I'll be there, and maybe Sharon will also be on there.
Awesome. All right, so if you're like, hey, how do I do this in terms of the quiz, you've got to actually go and put this link into your browser. So this guy. That's the link you're going to need for your quiz. And if for some reason you don't have access to a browser right now, you can also just do the quiz in your notes, and at a later point in time, send me an email with your electron configuration and orbital diagram. So no worries. If you run into technical difficulties, as scientists, we always iterate and innovate. we'll figure out a way. All right. So if you're wondering about additional resources in terms of learning, I've got a couple of really great ones for you. So I went through and I found some really great online supports. So if you want a review of the periodic table, there's a great resource here. If you're looking for electron configuration and ions, you can find that here. I put the link for chapter 6.5 and the periodic simulations and periodicity and trends. I will post a key this weekend for exam practice 2. And then if you have any questions about the quiz, I will hang out and be available if you have questions on Zoom. All right. I'm gonna stop recording.